Welcome to Group B15's research presentation. In this video, we will be covering the concept of metasurfaces, a general idea of how they work, how they are useful, and a few examples of how they are used in the real world. Before we jump into the topic of metasurfaces, it's best to first introduce the topic of metamaterials. Metamaterials are materials which are created to adopt certain properties not found in nature. This is achieved through a specific synthesis of composite materials, most of which are metals or plastics. For instance, electromagnetic metamaterials are composed of periodic sub-wavelength structures that resonate with the electric and/or magnetic components of the EM fields surrounding them. This characteristic of metamaterials interests a variety of fields of nanoscience because they can present us some unique yet useful characteristics. Examples of some characteristics is optical magnetism, where the material becomes magnetically polarized due to its interaction with light, as well as a negative refraction index, where the angle of refraction to the normal is less than 0.
I'm going to be talking about the theory behind metasurfaces. In conjunction with a metamaterial, a metasurface refers to a surface generated by a metamaterial. Like metamaterials, most forms of metasurfaces incorporate sub-wavelength structures into their design as a means of interaction with incident waves. They have the ability to produce abrupt changes over the scale of the incident wave's wavelength in either its phase, amplitude, or other associated characteristics. There are a variety of metasurfaces with different uses, thus the ways through which they are created are numerous and depend on the attribute of the wavelength that is being affected. For instance, certain optical metasurfaces are created through implementing an array of small light scatterers with spacing smaller than the wavelength of the incident light wave. In accordance to Huygens' principle, the light wave will be diffracted by the metasurface based on the spacing of the scatterers. As a result, the light wavefront can be controlled arbitrarily by changing the spacing between the scatterers. What you see here is a metasurface used for collecting electromagnetic energy. Thanks to modern nanofabrication techniques, we can now create nanostructured metasurfaces that control and shape light wavefronts. The metasurfaces that emerge as a result of this make it possible to tailor both the electric and magnetic response of light with sub-wavelength resolution, thus offering unprecedented levels of design flexibility and performance. Such metasurfaces can ultimately control and shape the amplitude, phase, and polarization state of the electromagnetic wavefront with extreme precision. Ultimately, reconfigurable metasurfaces may also provide a pathway to the full control of electromagnetic waves at will, with applications from radio frequencies to visible wavelengths and beyond. Here we can see how the reflected wave is neglected to minimize the reflections of the metasurface, assuming that a metasurface is located at z equals 0 and illuminated by an incident wave propagating along the positive z direction that is determined beforehand.
One of the most important uses of metasurfaces is the control of electromagnetic waves by imparting local gradient phase shifts to the incoming waves at the wavefront. These ultra-thin surfaces are used for the control of the phase, the amplitude, and for the polarization of visible light. As shown in this picture of a phase-graded metasurface, the phase of scattered light done by the nano V-shaped antennas can be controlled over a pi phase, oscillating from 0 degrees to 180 degrees and back. Essentially, this allows light to be manipulated in ways that cannot be done with naturally available materials. The complexity of the surfaces change the resulting properties that they produce as well. Take dielectric metasurfaces for instance. Polarizers and photovoltaics are both dealing in the visible light spectra but performing different functions. Polarizers on one hand allow certain wavelengths of light to pass through while not allowing others. Photovoltaics deal in the excitation of electrons from a lower state to a higher state, in which then they can become charge carriers. Also, silicon metasurfaces, a subset of dielectric, have various applications in the real world. While looking at power lines and how current flows, we can avoid Joule losses by using dielectric materials by avoiding the heating of overhead power lines. Looking at the absorption of regular light, we see the absorption spectra is quite small, allowing for very inefficient absorption. Using a metasurface allows for a wider absorption spectrum, allowing for more absorption and more efficiency. Photonics is another growing field that uses metasurfaces to increase efficiency and bring forth new devices. Through experiments and research, sub-wavelength metallic nanoantenna arrays patterned onto a surface can provide the basis for planar optical devices. These devices can be used over a wide range of industrial applications. Some of the devices include super resolution imaging, sensing, data storage, quantum information processing, and even light harvesting. All these devices encompass metasurfaces and what it can be used for. Now on to applications.
Metasurfaces have a variety of applications in the industry today. One of the applications is using metasurfaces in biomedical devices. Metasurfaces are being used to enhance MRIs to make them more efficient, accurate, and safe for patients. This is achieved by placing an array of metallic surface between the object and the scanner. Sub-wavelength manipulation is used to enhance the radio frequency of the magnetic field, resulting in less noise, improved image resolution, and increased scanner sensitivity. Another application of metasurfaces is being implemented at the Capasso lab at Harvard University. They have found a way to create achromatic flat planar lenses. Usually, color-correcting lenses require light to pass through several thick lenses. This improvement will allow color correction to be achieved in one ultra-thin device. It uses a dielectric material rather than metal, which offers improvement to focusing capabilities and it increases the range of accessible wavelengths. Within the device, there are light concentrating antennae, which are able to detect wavelengths and adjust based on the differences. The device deflects 3 wavelengths of light by exactly the same angle, then focuses them on the same point using the secondary device. As you can see here, the flat lenses are more efficient than a conventional curved lens. This is a major step forward for planar optic technology, as this device is lighter and highly functional without compromising efficiency. The Patanker Group at the McCormick School of Engineering has been working on methods to use metasurfaces to design a method to control heterogeneous phase transitions. In nature, raindrops collect on leaves and form droplets that roll off the surface. This is due to the water-hating nature of these leaves. The leaves have double roughness nanostructure within their makeup known as the lotus effect. The goal of the Patanker Group is to make hydrophobic surfaces from hydrophilic materials that will cause liquids to flow off the surface with low drag. This research has a significant impact on the development of self-cleaning surfaces. That concludes our presentation on metasurfaces. Thank you for listening. Goodbye.